All right, the quizzes are not graded completely yet. I will be getting those done hopefully this afternoon. So those of you who've taken it can get those, see your grades. But again, we've got a number of people have to do it yet, so we won't be getting those back for a while. So let's talk about this thing called use substitution. Now we have a gateway test in the near future. Right now that's looking like Monday. I was thinking about Friday for that, but I think it might work best to move that to Monday. We also are going to do a group paper. And we're going to be working on that during this time frame as well. So one day this week, I haven't decided what day that's going to be yet. One day this week will be devoted to letting you work in small groups on your paper. Now, you might be thinking tomorrow what I'm going to do is give you a chance to write down the names of 2 or 3 people that you might like to work with in a group setting. I'll try to honor those wishes as best I can, but I probably won't be able to completely. So I will give you that opportunity. So you might be thinking about that. Now, in the past, and I know we have some people, I don't know if anybody in here, but we have some people for state wrestling. Going to miss a couple days here, but in the past, it was always an issue. You probably had to get together, meet at somebody's house, sit down to type it, and so forth. But with Google Docs, we can, you can kind of make edits and change things and communicate kind of that way, which we didn't really have that opportunity in the past. So even if some of your group's gone over the weekend or whatever, you can have, you still have that collaboration, opportunity. Now, what the paper is it's a problem. It's like your group is a group of math experts. You are the consultants. You are the big shots. And this person and or fictional character has an issue, a problem that they need to have solved. And so they are going to be writing you a letter asking for your help in solving this dilemma that they have. And so your paper is your letter in response back to them. And we'll talk more tomorrow about how do you write a math paper, what does that look like, things like, it's not like homework where you're like a test question, you're trying, supposedly I'm the expert, and you're trying to show me that you know what you're doing. That's not what you're doing here. And you're not trying to teach, you're the expert, and you're not trying to teach this person how to solve the problem. You're solving it for them, and then you're giving them the result. So you're not going to go into great detail with all the nuts and bolts of how you solve the problem, okay? Because that's way above what they know. They are trusting you to do that. Now, there are some things you can do when tell them how you're approaching the problem, and you may have diagrams or tables or whatever with information that you give. But that's kind of the format. That's kind of what it's all about. And there's a rubric. I'll kind of have a rubric on there, so I'll hand you some information tomorrow about things that will guide you in doing it. Okay, and that'll probably be due middle part of next week. It's probably 2 to 3 pages at the most. That's if you double space, and whatever, and 3-inch margins. Can't have 3-inch margins, but so it's the length of it's not really an issue. If you go through if you follow the rubric and you include the information you need to include, that pretty much takes care of itself. It'll be somewhere in probably 2 to 3 page range. Okay. So anyway, that's what we got going on the next few days. So this idea of use substitution. So let's back up just a little bit. If you open your books to page 333. And okay, we have this list, this table of antiderivative formulas. So you need to be able to memorize these antiderivatives. The power rule, natural log, don't forget the absolute value. E to the x is its own antiderivative. If you have 2 to the x, you have to kick out a 1 over ln2. That's to offset if you do the derivative of 2 to the x, you have to tack on an ln2. So when you do the antiderivative, ln2 is just a number. When you do the antiderivative, you need a 1 over ln2. attached to it. That'll probably be the one you got to study on the most. Sine, cosine should be easy. Secant squared, the antiderivative is tangent. And then arc sine and arc tangent. We want to be on the lookout for those. If you see an integral that's got square root 1 minus x squared, that's arc sine. And you see an integral that's got a 1 plus x squared in the bottom, that's arc tangent. Every antiderivative problem we do, every one that you were assigned to do, after you did your u substitution, should have ended up looking like one of these, or a version of one of these. And every one we do will happen. The whole goal of doing antiderivatives is to learn techniques, and u substitution is one of them we're going to learn, that will turn integrals into looking like these. That's the whole idea. Okay? So now, when we go to, so let's just back up here a second. So if I give you a problem, let's see, there was one on the homework here. Number 10. Let's talk about number 10. Integral x over 1 plus x dx. Now, you had the advantage here of the book telling you what u was going to be. You enjoy that because it ain't going to happen anymore, right? You're not going to. You will have to not only pick what you're going to use for u, but you'll have to decide if u substitution is even necessary, as we'll get into on some today. Okay? And when we learn another technique that we're going to learn here in a day or two, you'll have to decide, is this one where I use u substitution, or does this need this other technique, or is this one I don't need any of those things at all? So that's what you'll have to be thinking about. All right, so what did they tell you to let u equal? All right. Now, for those of you that were here on Thursday, what was the only thing we've really talked about as a class so far of what you picked for the u? The inside piece. Right? The inside. Well, here's another strategy. Now, somebody in their class said, well, this could kind of be like the inside if you brought that up and it would be 1 plus x to the negative 1 power. That's true. You could think of it as being the inside there. Okay? But I like to think of it this way. This is just another strategy for what we picked the u to be. The bottom. Let u be the bottom. Either the whole bottom or a good chunk of the bottom. The inside. Those are the two main things that you let u equal. The inside of something or the bottom. Now, you don't have a lot of options on this one. I mean, let's back up even a little more. Does this look like anything on page 333? No. Is there any algebra we can do to this to make it look like page 333? I don't think so. Now, when I say that, I mean, I'm thinking of a problem like this. Does that look like anything on page 133, or 333? 1 over x cubed. Is it an ln? An ln is only what? 1 over x to the first. That is not an ln. Some people get in that habit every time they see 1 over something, they think it's an ln. No, that's only 1 over x to the first. Does this look like page 333? I don't see any that look like that. But what if I wrote it like that? Now it's a power rule. Now it looks like the first one, right? So there's always going to be integrals where if you do some algebra property or something algebraically to them, then they'll look like page 333. So we want to be able to do those, okay? But there isn't anything here. There's nothing we can do. Can I split this apart? Can I split apart this bottom? You can never split a denominator, right? Never split a denominator. If I have 3 over 3 plus 3, can I split that into 3 over 3 plus 3 over 3? Absolutely not. That'd be 1 plus 1, which is 2, and we can tell this is 3/6 or 1/2. That would not work. You can never split a denominator. Okay? All right, so there's nothing we can do to it. And there's not a lot of choices for what we could pick for u. Somebody in the other class said, what about let u equal x? Now, you kind of laughed. Why did you laugh? I'm not sure everybody understands why you laughed. And so what would what would happen?
Yeah, it'd just be.
It would be, right. In other words, let's think about this, because I'm still not sure everybody's seeing it. If I let u equal x, and any time I do a u substitution, what's my next step? The derivative, right? The next step is the derivative. So you guys, hopefully you got to watch the video from Thursday, but the next step is we do du dx, right? Except I don't write du dx. Why? You guys that were here. I'm going to move the dx over there anyway, right? So what I do is I don't write that. I just write du equals, and the derivative of x is 1, and then I would have this dx that I just swing over to that side. I do that every time. So when I pick my u, the next step is to do the derivative of u, which would be du over dx, which would be 1, and then I swing the dx, multiply the dx over to that side. So I just do it every time. Now I just write du for the derivative, do the derivative, tack on the dx. Okay. Well, as soon as you do that, now you substitute what's your integral. Well, if you substitute x for u, you get this. This would be 1 plus u, and the dx would sub out and be a du. And that's why you're laughing, right? Because what did you do? You didn't do anything. You got the same integral, except now you got u's instead of x's. So never, 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 in a u substitution, let u equal x. Never, okay? Now, in the new technique, the other technique we're going to learn, sometimes you do let u equal x. Okay, so you have to just understand to keep those things straight. All right, back to this. So what's the du, the derivative? 1, and then dx. Don't forget about putting on that dx. It's important. Okay, now we make our substitution. So we're writing a new integral. Hopefully it looks like page 333. So what I told the class on Thursday is I think you should circle the things you're substituting. So this 1 plus x is u. This dx is du. So far in the blue, I have substituted the two things that I circled, I have taken out and replaced with their equivalents. But I have this extra x up here. So what do I do with that? I take this right here and I solve for x. Right? So x would equal u minus 1. So in place of this x, I now have an x minus 1. Or excuse me, a u. In place of that x, I have a u minus 1. Now you might look at that and say, well, geez, big deal. That didn't change it much. It looks almost like the original. But it's much better than the original. Why? Now we can split it. So the whole reason that it's good to sometimes, that it can be good to let u be the bottom is that gives you a single denominator. And when you have a single denominator, you can split apart a fraction. So what we end up with is the integral of u over u, which is 1 over u, which I'm not going to write u to the negative 1 because I recognize 1 over u is what? ln, okay? And I got my du. Now a couple other little things that came up in the other class as well. Notice I wrote my integral symbol again because I haven't done the antiderivative yet. This integral symbol means do the antiderivative with respect to u. Okay, so that's what it's telling me to do. It's a lot like this. Well, I'll tell you what, let's finish it. So what's the antiderivative of what? Not x, it's u, right? It's with respect to u. Antiderivative 1 is u. Minus, that's along absolute value of u plus c. Now we're not done yet, but does anybody have any questions on that step? None at all. Here's what somebody said in the other class. Somebody asked what happened to the du when we went from this step down to this step. What's that? Well, it's not really derivative. I mean, I know in here we did derivative. That was du over dx, but I think the way to say it is that the du is only there as part of the notation telling you to do the antiderivative with respect to u. And maybe it didn't bother anybody, but I think every year it bothers some people, and then they don't say anything. They look at this and they're like, well, when I do the antiderivative, what happened to the du? I would equate it to this problem right here. If I ask you to do this problem, okay, I said, okay, give me the answer to this. What would you write? Now, would you be bothered, or would you think to yourself, what happened to the dx? No, because what you do is this says do the derivative, and this says with respect to x. So you do the derivative with respect to x, and you get that. The dx just goes away because it was there telling you what to do. Well, that's the same thing here. This is the integral. This is saying do the antiderivative with respect to u. That's what we do, and that's why the du is not there anymore after you're done. Just like that derivative. Okay. But we're not done because we do need to put the x's back in. So in place of u, we'll put 1 plus x. And in place of the u in here, we'll put 1 plus x. And then plus c. And did anybody try to check this one on their calculator? Why don't you get your calculators out and let's do it. Because the calculators can be a nice thing when you're working at home, studying for the gateway test, practicing these problems. You want to check and see if you got it right. And it's an even problem. It's not in the back of the book. Get out your calculator, have the calculator do it. Now, we've got to understand, as has happened to us before, sometimes a calculator will simplify things in a way different than what we're getting, and we might think we're wrong when in reality we're right. So, let's talk about this one. First of all, I'll bet inside the bars here it's got x plus 1 instead of 1 plus x, doesn't it? Okay, because they like to write it in highest power order. So they wrote that as an x plus 1 instead of 1 plus x. No big deal. What else is different? They don't put a c on these problems. Yeah, they don't. When they do an antiderivative, they don't tack on the plus c, so you have to do that yourself. The 1's gone. Why? It's part. It what?
Nothing.
Why is the 1 not there? It's part of the plus c. In other words, c is just a constant added on, and so is a 1. So a 1 plus a c is just c, which seems kind of strange. 1 plus c is c, but in this case it is, because c is just any arbitrary constant, so a 1 added to any arbitrary constant is just some other arbitrary constant, so we can just use c to represent that. Okay? It seems strange that c could represent two different things, but it represents many different things in this case. Okay? Now I'm okay if you leave it like this with the 1. Right? If you want to take off the 1 when you write your final answer and just say that it got absorbed to the c, I'm okay with that as well. Is that weird to say absorbed? I don't know. I think it just did. Consumed. Consumed. All right. So there's a little bit. So this is a little bit different than what we had worked earlier. Let's do another one. Somebody got another one on the homework they wanted to ask about. We will wait on 11 and 13. We'll come back to those. Anybody else?
24.
Which one? 24. Okay. Antiderivative. Now, again, let's not forget about our notation. Let's review this. Integral without any limits on it, right, is called what? An integral that looks like this is called what? Indefinite integral. This is an indefinite integral. And the idea being that if there was a 2 here and a t here, then this would be an antiderivative, but we'd be able to find the c, right? We'd be able to find the c because of this left endpoint. So this would still mean antiderivative, but it would mean then we could do the antiderivative, put in a 2, we could find the c value that way. Okay, or we'd know that big F of 2 was 0, that whole thing that we did last week. All right, so the idea on an indefinite integral is we don't even know the left endpoint. So if we don't know the left endpoint, then why even write anything? And so we don't write anything. This just means it's the antiderivative, it's all the antiderivatives. We don't even know the c, so we just put on a plus c. All right. So on your gateway test, of the 10, 7 or 8 of them are going to be like this. 2 or 3 will be definite integrals. like 11. What's the answer to a definite integral? A number, because a definite integral is a fixed piece of area. So a definite integral is a number. All right, so you've got to decide, what do you pick for u? What do you think? The inside, right? The first thing you usually think of for a u is something on the inside. So don't make it harder than it is. If there's something on the inside, that's a lot of times what it's going to be. Okay, what's the du? Negative 3 dx. And again, that comes from du dx. And then we just move the dx over. All right, so now we're going to make ourselves a new integral. Except instead of u's, we're going to have x's. So this will become what? The red circle will become sine of u. And we want to get rid of the dx. So what do we do here? We're going to divide this over here to the other side. And that will be, and that happens a lot. You'll get these constants in here when you do your derivative that don't matter. I mean, they do matter. They're important in the final answer, but they don't matter as far as what you pick for your u, which we'll get into here in a minute. But because we can always move those around. Okay, so that negative 3, I'm going to move over to there. So the dx will get replaced with a negative 1/3. Constants always go out in front, and the du always goes at the back. Okay, so negative 1/3 there on the left, and the du, it's perfectly fine to do that. And there we go. Yes?
So if you don't move the constant outside of the interval, does that change the answer?
No, if you left it in here, that'd be fine. It just, yeah, either way is fine. Either way is fine. Okay, this just reminds, it's just like doing derivative, just reminds it's just going to hang out here when we do the antiderivative. But yeah, I'm fine if you leave it in. So the antiderivative sign is negative cosine. So that turns to positive, and then plus c. So this would be 1/3 cosine 2 minus 3x plus c. Now, did you need to do u substitution? No. We did antiderivatives like this. We just didn't put a definite integral in the dx with it. But we did antiderivatives like this back in chapter 2, or chapter 3, when we first learned these rules. Because if all you have on the inside is a constant times your x, you can kick out the reciprocal of that. Remember that? So when we were doing derivatives on this, we said, hey, we got to kick out a negative 3, derivative of the inside. When we do the antiderivative, we'll have to kick out a negative 1/3. So we could have done this one without any u substitution. We'd have just had to kick out a negative 1/3. But now you can see why the negative 1/3 got kicked out. You can see where that comes from. So my hope, I don't really care, it doesn't matter to me, but on the gateway test, if you see this problem and you know you just need to kick it out and want to write your answer down, I'm fine with that. You don't have to do u substitution, just show me you can do it, right? I'll give you problems that need u substitution and you'll have to do it, okay? If you get one like this, you wouldn't need to, okay? And matter of fact, it's helpful. It's helpful if I give you this problem right here, it's helpful that you know when you do that antiderivative, you're going to kick out a what? A 1/2. It's going to be really in your best interest to see that if you've got e to the 2x, that you know you'll kick out a 1/2 and not have to go through u substitution, because what's going to happen is we're going to have e to the 2x's and e to the 4x's and sine 4x's inside of problems that need a bunch of other stuff. And if you've also got to do a u substitution just to handle that, it's going to get really messy. So it's nice if you can just look at that and see that. Okay, that'll be helpful too. All right. What's another one? 26. Okay, that's a good. X cosine of 1 minus x squared dx. Okay? So, we're going to let u equal. Now, I told you that you're not gonna have the advantage of them telling you what to pick for u. You've gotta choose the u. So let's talk about that thought process a little bit. You guys picked 1 minus x squared because I told you what? Choose the inside. I want you to go beyond that a little bit here. I want you to be thinking a step ahead. This is what you should be thinking when you pick a u. You should then be thinking of the du. You should be saying to yourself, okay, in this problem, if I pick u to be 1 minus x squared, what will the du be? Negative 2x dx. Now, do I have a negative 2x dx there? No, but the negative 2 I don't care about because I can move that around, right? That's like that negative 1/3. The constant I don't really care about. So when I'm thinking of this problem, I'm saying, you know what? If I let u be 1 minus x squared, my du will give me an x dx. Yeah, it'll be negative 2 dx, x dx, but whatever. There will be an x dx. And what have I got? I got an x dx right there. See, that's what I would be looking at in a problem like this. So the reason this is just a tailor-made u substitution is because of that x set right there. If I take that away, you can't even do this antiderivative. There's no technique in the world that will do this antiderivative. Okay? But if I put an x right there, I can. And that's the whole thing. So I look at this, I go, oh, okay, this is a good one. This is nice. Because I'll let u be 1 minus x squared. And so I'm thinking that in advance. And then I say, yep, I think this is going to work. Now I got to get into the details. How's that negative 2 going to fit in there and what will happen with it? So here we go. So we get the du. We get negative 2x dx. We go to make our substitution. So now I start circling things. Okay, that right there is going to circle, is going to sub out as cosine u. Now, what I would do with this is divide the negative 2 over there. Did anybody divide the negative 2x over there? Did anybody think about dividing the x over there? A few people in the other class did. Now, my typical response to that is to avoid doing that. I think in general, if you just don't mix the x's and u's, you're better off. However, it works. It'll work. Here, let me show you what happens. Normally, this is what I would recommend doing. I would move this negative 2 over here as a negative 1/2. And I've got x dx right here. Because what I notice is that I have an x dx right here. So x dx is going to get replaced with negative 1/2 and du. Okay? Now, Robbie, correct me if I'm wrong, but this is what somebody in the other class thought. Somebody in the other class thought they wanted to sub out the dx, so they thought it would be good to get the dx by itself. So they did the du divided by negative 2x like this. Now, I would probably write it as negative 1 over 2x, dx, du, and then that was equal to dx. Now, I just don't like mixing up the x's and the u's, but let's think about this. So we sub this out, and now we take the dx out, we bring over negative 1 over 2x du. What happens to the x's? This x and that x over there will cancel, this x right here will cancel, and you end up with the same thing. And if u substitution is going to work my way, if you do it that way, it'll work too. Okay, so I wouldn't count that wrong if you did that. I just think in general, you're better off if you don't mix up x's with u. You leave that over here. Okay, like so. All right, anyway, antiderivative cosine is sine, so this is negative 1/2 sine u plus c, and then you put your u back in, and so we get sine 1 minus x squared plus c. Okay? All right. We have another one. Thought there was one. Maybe this is one we'll do a little later here. No, I don't remember what it was. Any others? What about 33? That was okay? Was that one we had to do? 43. Okay. Well, I want to practice a few here. Anyway, so let's go through here and talk about 11. Let's talk about what happens when we get a definite integral, how that changes things. All right. Now, question 11 was asked in kind of a funny way. They said, here's this integral, and then here's this new integral, and what's the a and the b? And so we want to talk about what that's about. I did help a few people with that in class the other day, but this is pretty important, so let's go through it. So we have the integral from -2 to 1. We have x over 1 plus x to the 4th dx. And then they give us this new integral, and let's just ignore that for a minute. But actually, I'm sure you looked at that, which actually was a good hint for what you should let u equal. You can tell by their second integral what they let u equal is what? X squared. Now let's talk about that a minute, and let's pretend that they had not given you that nice hint. How in the world would you have thought to let u equal x squared? You know what I mean? I mean, let's face it, I think with what you guys know right now, you wouldn't have, right? You wouldn't have had any clue. So let's talk about the things we've talked about. We said let it be the inside of something. There isn't any very obvious inside of anything there. We talked about let u be the bottom. So let's think about that. So the thought process would be, all right, I'm going to let u be 1 plus x to the 4th. What's your next thought? What's the du? What would the du be? 4x cubed dx. Is there an x? I don't care about the 4, but is there an x cubed dx there? No, there's an x dx, but there's not an x cubed dx. So that's a bad choice. Okay, now if this was an x cubed, this would be a great u substitution problem, right? Just change that to an x cubed right there, and then this would be just a real basic, fundamental u substitution problem. Okay, but it's not. All right, so then, and part of our work this week is exactly this, just like the other gateway test. Working enough examples that you start to see all the different little quirks and all the different little things that can happen. And this is one of those. Look at page 333. Look at the bottom rule on page 333. What do you notice? You've got an arctan, right? And what's the bottom on arctan? 1 plus x squared, or for us, 1 plus u squared, right? So add this to your list of things you're looking for. When you get an integral, and you're doing an antiderivative, if you've got a 1 plus something on the bottom, if you can somehow get a 1 plus u squared to happen, you're going to have an arctangent. Now again, if this was x cubed up here, we wouldn't even think of that. We would just do a straight, let u be the bottom, and there we go. But now, since that doesn't work here, our focus shifts to, you know what? I can make this a 1 plus u squared if I let u be x squared, because this is x squared squared. And the other good advantage of letting u be x squared is what? The du will give me the x dx. And so that's the thought process I would go through in coming up with letting u be x squared. I would have recognized an arctangent hiding in there. And then don't do like somebody who will not mention Jake Kingsley's name, but do not think that 1 plus x squared squared is this. Right? It bothers me that a few of you are going, it's not. You're thinking, what? You can't distribute a square, right? That would be a FOIL. So he's thinking you could let u equal 1 plus x squared, and then that would be the whole bottom squared, and that's not. So don't make that algebra mistake. That would be bad. Okay, so on to this. So all your work on 11 should look like this. Now the 2, I'll move over to here. You get x dx, and now things should sub out pretty nicely. The x dx comes out as a 1/2 and a du. Now keep in mind that this dx is always, think of it like a fraction, it's on top. Like if you have 3/4 x, that's the same as 3x over 4, right? The x could be out in front of the fraction, or it could be, on top. It's kind of the same thing with the dx. So this is like an x dx here. That's a 1/2 du, subs out. What about the bottom? 1 plus u squared, and since there's nothing left on top, we have to put a 1. Now, I would say to you, though, look at my problem, look at the problem, look at the blue circles. Have we subbed out everything? We have not subbed out these numbers. Those have to sub out. Those are x values. Think about it. This definite integral is some graph, from -2 to 1. -2 and 1 are x values. So we take out the x's and put in u's. We've got to take out these x values and put in u's. How are you going to do that? Substitute them right there. Yeah, take -2 and put it in for x, because they're x values. So take -2, put it in for x, and that's 4. And take 1 and put it in for x, and that's 1. Now it ends up being backwards, but that doesn't matter. 4 to 1, whatever. That's what we want. Okay? So this is 4 down here. This is 1 up here. The thing about doing this, then, is we don't have to go back to x's in this problem. Because what's our next step in a definite integral? Do the antiderivative, right? In a definite integral, it's big F of b minus big F of a. Fundamental theorem part 2. It's do the antiderivative, plug in your b, plug in your a. So, what's the antiderivative of 1 over 1 plus u squared? Arctangent. So this is 1/2. Now, I know they didn't ask you to do this on this problem, on 11. They only wanted you to figure out what a and b were here. Okay? So the 4 and the 1 would be your answer. But let's keep going, because that's the kind of problem we're going to have to do in the gateway test. So we got our 1/2 arctangent u. We don't put on our plus c, because remember, that'll subtract away. Right? So at this point, it looks a little different than an indefinite integral. So we do our antiderivative, we put on our right bracket, and now we do f of b minus f of a. So this is 1/2 arctan of 1. I mean, we don't need to go back to the x's, because we're just going to end up with a number answer. And 1/2 arctan of 4. And that is not good enough. We need a number answer, which means we want to simplify it as much as we can. We can simplify this a little more. Now this would be one of the harder ones. Remember the gateway, we talked about some easy, some medium, some hard. This would be hard because there's just a little more you got to do. Arctangent of 1 is what? No. Where does tangent have an output of 1? Pi over 4. Arctangent is 1, because that's when the cosine and the sine are the same at pi fourths, root 2 over root 2. Okay? Root 2 over 2 over root 2 over 2. So this would be 1/2 times pi fourths, which is pi eighths, minus, and then arctan of 4 is not one we would know. Any number that's just a unit circle number, you need to know. So on page 333, we have two antiderivatives that have trig in it. We have arc sine and we have arc cosine. Well, we also have the regular sine and cosine and tangent ones as well. So if you get a sine, a cosine, and a tangent problem, and it has you plug in a pi 6 or a pi thirds or a pi fourths or something like that, you've got to simplify those. You've got to know root 3 over 2 and 1/2 and 1 and -1 and 0. And root 3, like if this had arctan of root 3, that's one of the unit circle numbers. You better review those unit circle numbers. Not that it will be a big deal, but it may come up. And you miss one, you're going to miss 2 on the gateway test, right? So you'd have to go to that point on that one. I think if you type that in your calculator, it comes out like that. Or similar to that. Okay? Now, you could have, I don't like to make the big deal about this, but you could have done this. You could have avoided the whole numbers, changing the numbers to a 1 and a 4 by going back to x's, right? What do we normally do in a problem like this? We take our 1/2 arctan, we take the u out, and we go back to the x squared. So I could have done this. I could have done this when I got my 1/2 arctan u. I could have done 1/2 arctan x squared, use my original x numbers, and what do I get? Put in a 1, well, we better get the same thing, right? 1/2 arctan 1 minus 1/2 arctan, and then you put a -2 in, and you square it, you get 4. So it doesn't save any, neither one of these is any shorter than the other. In this one, you had to plug your x's in here to get used there. Here, you ended up plugging them in at the end. Okay? Still comes out the same answer. Okay, so I don't care, but when you work it, I don't care which way you do it. But let's say on the final, on the AP test, they might do a multiple choice question like number 11. They give you this original integral, then your choices are all this integral with different numbers in here, and you've got to figure out how those numbers came to be. So you need to be able to do that. All right. Any others? I want to put some up here and let you practice them, and then we'll talk about it. If there's not any others. Cody? Yeah, 13 would be basically the same thing. Yeah, it would just be essentially the same thing. What would you let u equal on 13? The inside of the bottom. Okay, the inside of the bottom would be the key. Well, I tell you what, we won't go through the whole thing, but it's if you've got it says x. And you've got this here. Okay, to me, the first thought's always the inside. When you let u be the inside, the 2x squared plus 1, the reason that's going to be good is what's the du going to be? 4x dx. And right there is an x dx setting there. So that's going to make that good. If I let u be the whole bottom, now that's a mess, right? Think about this now. If I let u be the whole bottom, then the du is going to be a 3 with this left alone to the second, then times a 4x, right? And it's just going to be a big mess that's not there. So that's why that would not be a good choice. All right, so the du is going to be 4x dx. The 4 is kind of in the way, so I'm going to move it over there because I don't have a 4 up there. Okay, and so my new integral, my x dx, would be this right here, 1/4 du. I don't have anything left on top, so that'd be a 1. What do I got on the bottom? U cubed. So we would make that u to the -3, right? And so we'd have our 1/4. We'd raise that up to a -2. We would divide by -2, which is that. So what do we got? -1/8. U to the -2, and then do your right bracket. Change those numbers. Is that a 19 and a 1? Okay, and then go from there. All right. On page 341, there's a number of problems that we will be working on throughout the week, as well as the LH packet. Let me find one here. We'll start a little easier. How about this? Okay, let's try number 55 on page 341. 5x over. Now, feel free to talk with each other, compare notes, ask each other. Okay, we'll just take a few minutes here to go through a number of examples and let you practice. All right, ready for the reveal? Don't look. Then I'm going to put it up here, but don't look if you're not there yet. That was like a warning. Yeah. Okay, here it is.
It's just little cool settings things, and I got the heart by itself on the screen.
Oh, to get rid of the axes and all those things.
It was really annoying to get rid of all the text where it said like 0.1 and where all the zeros were or whatever.
So there was a lot of different settings you had to go to.
Yeah, just a couple, and I just had to like select some things and hide them. But yeah, it was fun.
That's cool.
Calculator tricks. I watched that happen, and I could do nothing to stop it. It had it coming.
Okay, comments, questions about this one?
I got it. Well, I guess.
Yes, Callan.
If this would have been like a gateway test, would you have taken off points if we didn't have absolute value?
If you
If it's just
didn't,
natural log, if we didn't
Possibly. In this problem, I would not take, look at my answer. That's what I was wondering if anybody would ask. Well, how come you don't have absolute value bars around? Let's go back to this one. If you did not have absolute value bars around this one, you would be wrong. And you would miss it. Okay? On this one, why don't you need the absolute value bar? Well, it's not just because it's squared. Because if that was 3x squared minus 4, then you would need to have the bars. If this was 3x squared minus 4, bars would have to be. So it has to be positive, right? X squared has to be positive. Times by 3 has to be. What's the smallest 3x squared plus 4 can be? The smallest it can be is 4, because x could be 0. Now, x can be negative too, right? X can be anything, right? X can be anything in this. But if it's negative, then it's almost like being a positive, right? The smallest it can be is if x is 0. This will have a value of 4. But if that was 3x squared minus 4, see, then that could be negative. So you'd have to have bars around it. Now, so to play it safe, just put the bars every time you do an ln and you'll be good? Yes. If you would have left bars on there, I would not count it wrong. They're there. They're okay to be there. They're just unnecessary because the thing in the bars is always positive, so the bars don't really do anything. But if you want to put them, just to be safe, that's fine. What's that? Yeah, so just do it. But I think it's important to understand why, because here's the thing. If you're at home and you're doing this on your calculator, the one earlier would have bars on it. This one wouldn't have bars on it. The calculator would know that, and it would not put bars on it. So you want to know why it did that. Okay? Here's the next one.
You should turn here. This one's the one where you just like split the denominator, right?
Don't you dare. Don't you dare.
Oh, you're making a joke. I was like, don't tell me. I haven't read it yet. That's fine.
Now, be sure, if you're not sure what to do here, talk it over with someone. Go stand up, walk over to somebody and look over their shoulder. Something. Okay, help each other out. You butt dialed Siri.
She goes off all the time because I have this little button so it sticks out. It like all the time. This is Days Lost.
What are we letting U equal? We don't know?
X minus
Okay, that's way too quiet in here then if you don't know. Too many of you are just giving up. You're just not doing anything. You're going to wait for me to work. Talk to each other. Throw out some ideas. There's not very many ideas. I mean, I couldn't let U equal a 17 here, right?
Why not?
Well, did you try that? No, you didn't. You're sitting there staring into space.
Wait, that's
What would be something we could let U equal?
-3.
X minus 3, because that's the bottom. We talked about that. What else could U even equal? X squared. Why wouldn't we do that? What's the du? If u is x squared, the du would be 2x dx. Is there an x dx sitting there? No. There's an x on the bottom, but it's with a 3, and that wouldn't be x dx anyway. That'd be a 1 over, because the x is on the bottom. So the only viable option is let u equal x minus 3. Okay, get that far. And sub out everything you can by doing that. Right? You can do a lot by doing that. On these problems, sometimes you're going to go down a road. You can't sit there and say, well, I don't know what to do. It's like you come to a fork in the road. You can just sit there and just be stuck there all day. Or you can go down one road and maybe it's a dead end. Get as far down the road as you can, and then you run into a dead end. You turn around, you come back and take the other one. That's going to happen in some of these. But don't just sit there and say, well, I don't know where to go, so I'll just sit in my car. Do something.
When was the last time you just sat in your car?
I did. You're right. I would take one of the roads and see where it leads.
Because that's pretty.
It's for all you like doing it. I got
What
you.
if it leads you off
That is such a cheerful look at
You're just driving down this road and then you go.
Alex, you got something?
You can't turn
Oh,
around.
Do you? You guys got it?
You're dead.
They have an LN in it
Absolute value.
Yeah.
with an absolute value.
I honestly don't know at this point. That's about as far as I got. And I got confused with the derivative.
What?
Yeah.
Pretty sure that that's why I'm
I got that part.
All right. I heard that, Melissa. Okay? Got that far.
So, I don't want to know the answer.
I'm not going to say it, but listen. So you do what we've talked about so far. You said you're going to let u be the x minus 3. So the du is the dx. So in red, I've circled what we can sub out, right? And so this is why I like circling things, and the colors are nice too if you happen to have different colors you can use. But so I've circled those two things. I've taken care of those. What have I not taken care of? The x squared. I got this extra x squared. Now, we've had a problem like that. We did it earlier today. We had an extra x hanging around right here. in this problem, we subbed out this x plus 1, and then we subbed out this dx, and we had an extra x hanging around. What did we do? We took this thing and solved for x, and we got rid of it that way, right? Isn't this the same thing? Same thing, same exact thing. So we did all that, and we looked and we said, oh, there's an extra x hanging around. So I can solve for x, so do it. Yes. Not very far. In other words, once you have your antiderivative with u and you plug the x's back in, I'm pretty much saying you're done at that point on an antiderivative one. Now, if it's a definite integral where you're supposed to get a number answer, we want to simplify that number down as far as we can, like with the sines and the cosine. But as far as like if you get a, oh, I don't know, just pick something out of the air, like a 6 times the quantity x minus 3, for example. Leave. Right? Because didn't you get that in? Close enough.
Don't laugh.
Kind of like-
Messed up. It's like, oh, just I did it right.
Just don't check. Just don't check.
Yeah, good point.
Then you might not be right.
Well,
You're all of your hopes and faith.
it might, you still might be right, it just might be written in form.
I think I shall leave you.
All right, I'm going to put it up here now. All right, there is
That was very smart of you.
the one in the blue there. Yeah, couple of things here. Couple of things. If you go, once you get down to the u's and you do the antiderivative, and then you plug the x's back in, this is what Cal and I were just discussing here. I'm okay if you just stop there. I mean, yes, we could distribute the 6 through here. At this point, we'd just be rearranging things. Okay, so I'm not concerned about that. Now, if this was a definite integral, like that arctan one we have, if you have a definite integral that's supposed to come out a number, you want to get that simplified as far as you can. I mean, once you get down to ln3, you know, or pi, you know, 6 pi, I mean, leave it like that, that's fine. But we had arctan of 1, and that's pi fourths. So to me, you can simplify that. But arctan of 4, we couldn't simplify, so we just left it arctan of 4. Okay, in these, we'd just be rearranging stuff. So I'm okay with you just leaving this. Okay, at this point. But now let's talk about the things that led up to that. Okay, so once you got the hang of the fact that, hey, we got this extra x hanging around here, we need to solve for x. So let x be u plus 3. So then you got u plus 3 squared. You FOIL that out. Why is this a good thing compared to the original? Because it's on top, you can separate, and you have a single denominator. That's why letting u be the bottom is a good thing. So this doesn't look that much different than this, but this one's way better. So we can FOIL it out, we can split it apart. U squared over u is u, 6u over u is 6, 9 over u is just 9 over u, because that's an ln. Remember, ln's are only if it's u to the first. So we get 1/2 u squared, antiderivative of 6 is 6u, antiderivative of 9 over u is 9 ln u, and then we put the x minus 3's back in. Okay? All right. So, but this is fine. Leaving it here is fine. Because FOILing that and then combining some terms, yeah, you could combine some things, but it's mostly rearranging. So this is good. All right, let's do 2 more. One more really. this is not a number, no, from the book. I actually took one from the book and kind of changed it a little bit to fit a little better with what we're doing right now. Okay, so that one go a little better? Yeah, I know. Isn't it kind of the same as the last one? I mean, in a general kind of way. What are you going to choose for u? It's the inside, right? I mean, so that's really the only logical choice. But if you let u equal x plus 2, then the du is just dx. So that subs this and this. You got an extra x hanging around. So what do? Solve for x. So you sub this out, you get u to the fifth. You sub the dx out, you get du. You've got this extra x hanging around. The extra x is u minus 2. Why is this better than the original? Again, this is where it's like the last problem. To me, what we end up with when we do our substitution looks very much the same as what we started with.
Except that you don't have to FOIL it.
Yes, we cannot do algebra to this. I cannot distribute the x through here. You would have to FOIL this. Now, if this problem would have been x plus 2 squared, I probably would have FOILed it, distributed the x, and then just done it that way, and not even done a u substitution. But since it was the fifth power, I didn't want to do that whole big long FOIL on it. Now, will somebody on the gateway test? Maybe. Somebody on the gateway test will do a whole big long FOIL to the fifth power, they'll distribute the x, and then they'll do the antiderivative, and they'll get credit if they don't make any mistakes. But there's a lot of places you can make mistakes. But the advantage here is we now can distribute the u to the fifth through there. Then we can do our antiderivative. Raise that up to a 7 divided by 7. Raise that up to a 6, divide by 6. 2 6 would be 1/3. And then put your x plus 2 back in for your u. Yes, Logan?
Did you take the parentheses minus 2 and take that out?
Say that again. Here?
Yeah,
Kick it out where?
outside the integral.
No. What advantage would that be?
That way you could do the integral to the bottom.
Oh, no, because that's a variable. You can pull a constant outside of an integral, but not the variable. And as a matter of fact, I should have said this because this came up in the other class, and I bet there's some people sitting here thinking about this. Why didn't you just do the antiderivative of this and the antiderivative of that? Because it's multiplication. You can't do that. I mean, it'd be nice if we could, but if I had e to the x times sine x, and I asked you to do that antiderivative, right now you don't know how. You can't do the antiderivative of each one of those individually when it's multiplication or division. You can't. Just like you can't do the derivative of a multiplication division. We got those special product quotient rules. Okay? There is an antiderivative to this problem, but you don't know what it is yet. We can't use u substitution on this one, right? I mean, this is a little peek ahead, but we definitely can't just do their individual antiderivatives for sure. That doesn't work. If you've got a plus sign between them, you could. But think about your thought process here for a u substitution. What could you let u equal? Well, no, you never let u equal x. But you could let u equal e to the x, right? Well, let u equal e to the x. What's du? E to the x dx. Do you have that setting there? Well, kind of. I got an e to the x dx, but I was already using that for the u. And do you have any way of getting the sign subbed out? You can't turn an e to the x into a sine. So you let u equal sine x, and your du is cosine x dx. That's not sitting there anywhere. So here's an example of one where you can try u substitution, but nothing would work. So all these ones we've been doing have been specially set up so that u substitution works nicely, right? But you can tell that there would be a limited number of those. I mean, there's a lot out there that you could make up that where u substitution just doesn't work. Okay. Well, remember, u substitution is really chain rule in reverse. So if the original function was not a chain rule, then your antiderivative is not going to use u substitution. Okay? All right. Here's the last one. You can probably do this one in your head. What would it mean? Negative.
Signpost.
Signpost. Oh, plus C. Yeah, I said that plus C. Plus C. Signpost. Former student of mine sent me that one time. College professor gave it to
I thought you were going to say he's a college professor now. I was like,
me. No, the
oh,
college
nerds.
professor gave in their college class they had this, and so she emailed it. She emailed it to me. So I thought it was good. All right. All right. So your homework. Here's your homework. Look at your assignment sheet, please.
I don't know how many times I've said that. Or I would prefer this year to be so
All right, so on your assignment sheet, like I showed you at the beginning of the period, there is this LH, this new LH packet. I'll have those printed off for you by tomorrow. There's a new LH packet. It's posted as a PDF, so you can grab the problems from there, just put them in your notebook. That's page 310. Just this line right here of this LH number. There's more, but in the LH, it's just this page 310 line right here. 7, 9, 16, 19, up to 58. Okay, so just LH, page 310 right there. Okay, so that's the PDF that I put on our website. Then in the book, right above it here in the bold, that book page we were just on page 340, I said do some of the ones, kind of like when we had that big page in our derivative review where you just pick and choose and do some. I would say at least 5 to 10 at a minimum off of that page. Just randomly pick some and do those, along with these in the LH pack on page 310. Okay? Practice, practice, practice. Is anybody gonna be gone any time this week that they know of? Thursday? Friday? Okay. All right. I'm leaning towards Wednesday,
Wednesday.
being the day we work on our group papers, because maybe it seems like that'll be a day most people will be here. So. We'll talk about those a little bit more tomorrow.
I heard the quiz yesterday, Friday was pretty easy.
I thought so.
Well, you're also the.
Yeah, I got like an 89 on it. I thought it was pretty good.
When you were in first grade or like?
No, when I made the key.
Oh, okay. I'm just glad that I don't have art tonight, and I'm just gonna be spending lots of time doing calculus. And that wasn't even sarcastic. I'm actually gonna spend lots of time doing calculus. I think we'll have time for this tonight. I might just make my friend's puppy. I'd rather go see my friend's puppy than to do calculus. Is that wrong with me?
Yeah, that's hard to beat.
I'd rather see my
Puppies are
friend's
good.
puppy
Puppies are good.
and do calculus.
Yes, I was gonna say. I think
Why are
what would
they-
be better than seeing your friend's puppy? Seeing your friend's puppy and doing calculus. Yes, exactly.
Yeah, that just made my night like 10 times
That's
better.
right. You have your cake and eat it too. Right?